Assalamu alaikum. Bismillahirrahmanirrahim. I am the student of Mehran University of Engineering and Technology, Jamshoro, Sindh, Pakistan, and by pursuing my bachelor degree in Metallurgy and Materials. My name is Abdul Wase, and I belong to 19 batch, having roll number 38. Today my topic is from subject Materials Thermodynamic and presentation on the Maxwell relation in thermodynamics. Actually, the Maxwell equations will be discussed in this presentation. So I have provided this content, which is importance and requirement of Maxwell relationships, and number two is for Maxwell equations and their derivation in thermodynamics. I will drive all these equations ahead. So discussing the importance and requirement of Maxwell relationships. The Maxwell's equations and their relationships establish the relation between various thermodynamic quantities like pressure, volume, entropy, enthalpy, temperature, internal energy, Gibbs free energy, and Helmholtz free energy. We have a lot. We say etc. Suppose we need to measure the change in temperature with respect to volume, having entropy constant, having pressure constant, in which we are interested, which are not easily measurable. Then we move to utilize the Maxwell relationships. I am giving you for example, for instance, is that if we are required to analyze the change in thermodynamic quantity or quantities, number of quantities with respect to other quantity at a constant temperature, what we have need, we are required some equipments. As far as it is concerning of not availability of equipments, instruments, and catalogs, and that are required to be used in analysis process. For this, we use Maxwell equations to determine the change in one quantity with respect to other, having constant number third. This kind of relationships between two quantities are discussed ahead in the form of equations. So these are the four equations of the and their derivations in thermodynamics. From one where U indicates the internal energy, which is change in temperature with respect to volume, having entropy constant, which is equal to negative change in pressure with respect to change in entropy, volume is constant. These all four will be derived individually. So moving ahead for four Maxwellic relationships in thermodynamics individually. For first, we are required a first equation, which is internal energy, which is equal to the change in temperature with respect to volume, having entropy constant, which is equal to the minus of change in pressure with respect to change in entropy, having volume constant. So according to thermodynamics, we are discussing all about material thermodynamics, so we must aware of the first law of thermodynamics and its equation. First law of thermodynamics all about which is a sum of change in internal energy and the pressure and change in volume. It means work done. So the equation one we have taken from first law of thermodynamics. Moving forward, for according to the second law of thermodynamics, which is change in entropy equal to change in heat divided by temperature, and we have just evaluating, we could get change in heat, which is equal to the temperature, and to change in entropy, which is denoted by dawa. Now we will put the change in heat value in equation 1. We will replace change in q with a temperature and change in entropy. So we have replaced, we got the this kind of frame in the form of equations. The temperature change in entropy is equal to change in internal energy plus pressure change in volume. So we will have just managed to get the actual equation. So we will transfer the p change in v to other side. We will get that change in internal energy, which is equal to change in temperature and change in entropy minus pressure change in volume, equation number b. As we know from the differential equation, we have already learned and their fundamentals. So similarly, we could have make the equation of Maxwell equation, which is change in m with respect to change in y, where x is constant, and then change in n with respect to change in x, having y constant. This kind of phenomenology used in the differential equations. This is one of the differential equation that is being used in all four equations. So Observing from question number B, we have assumed that m is equal to t and n is equal to p. For assumptions, we could form this kind of equation: the change in temperature with respect to change in volume having entropy constant, and then which is equal to minus of change in pressure with respect to change in entropy where volume is constant. This is here it is the derived first Maxwell equation. So we are moving forward for the number second. Number second is which is all about the equation taken from the enthalpy. We should aware of what is the enthalpy, which is the sum of internal energy and then pressure into volume where temperature is constant. So we have one variable which is independent, so we use by partial differentiate equation a with respect to u because u is independent. So change in enthalpy with respect to change in internal energy, and then change in internal with respect to change in internal energy plus so we have now to product derivation. So keeping v constant, change in pressure with respect to change in view, and then we are keeping p constant and change in volume with respect to change in internal energy. By evaluating, we have this kind of frame in the form of equation change in enthalpy with respect to change in internal energy. So evaluating and multiplying both side equation number b by a change in internal energy. So we have just to evaluate, must have two parameters that will make the Maxwell equation. So evaluating change in enthalpy divided by change in internal energy multiplied by change in internal energy is equal to change in internal energy plus volume change in pressure plus p dava v, which means change in volume. So we will cancel out these and we will have this form of equation, and then we have to make these three variables into two variables. So we know that change in internal energy which is equal to change in internal energy plus p dava v, which is equal to dava q, and dava q is also is equal to the temperature change in entropy. So we just replace it. When we replace these, then it will become this form of equation, the change in enthalpy which is equal to T dava S plus V dava P, and this is the equation number D. So now we have to just use the differential equation on these two terms. We know the differential equation, we have just to make M, keep in M dava X plus N dava Y. So evaluating this, we could have this form of equation: change in m with respect to change in y keeping x is constant, and then change in n with respect to change in x keeping y constant. Observing from equation D, then we have to just make equal m is equal to t and n is equal to v. Similarly, by following the differential equations fundamental, we can form number D equation in this form: change in temperature with respect to change in pressure, entropy is constant, and then which is equal to change in volume with respect to change in entropy having key P constant. It is now derived the second relationships. Uh, number three Maxwell relationship, which is all about Gibbs free energy. We must know the definition of Gibbs free energy, which is H minus temperature into entropy, where I would guess the pressure will be the constant. And so evaluating it by differential equation by partial differentiate, then we will have a change in Gibbs free energy with respect to change in enthalpy. Here the enthalpy it is independent, and we will have to differentiate with respect to change in enthalpy. So change in enthalpy divided by change in enthalpy will be equal to 1, and then we have to use the formula of product, formula of derivation in partial form. So this is the keeping S constant, change in temperature with respect to change in enthalpy minus keeping temperature constant, change in entropy with respect to change in enthalpy. So the equation number B is formed. So by following same process, we have just to multiply change in enthalpy from to both sides. Evaluating, we will get change in Gibbs energy, which is equal to change in H enthalpy minus entropy, change in temperature minus temperature, then change in entropy. We have found C equation. So we know that we have just replaced the change in H with some other form. So we know that change in enthalpy, which is equal to T dava S plus V dava P. We have just to put it on the place of change in H in equation number 3. So we will have a Gibbs free energy, which is equal to change in Gibbs free energy, which is equal to V dava P minus H dava P. So just following the same process of differential basic fundamental differential equations basic fundamentals, which is that m dava x plus n dava y. And so evaluating and making m is equal to v and n is equal to s. Then change in volume with respect to change in temperature, keeping pressure constant, is equal to minus change in entropy with respect to change in pressure having temperature is constant. This is number third relationships. We have just simply followed the differential equations fundamentals. So we have evaluated each and everything. Here minus comes from the equation C, where we have to move n dava y to other side, that cause to have a minus on the number 3 relationship. Number fourth, Maxwellic relationship. Here we will discuss all about Helmholtz free energy. Helmholtz free energy is also denoted by F, but we are here to denote it A. It is also denoted by both F or A. You can use what suits to you. So A is equal to U minus temperature into entropy. So partial differentiative, we have just partial differentiate it with respect to U, because internal energy is independent of every variable. So we will have to just partial differentiate change in Helmholtz free energy with respect to change in internal energy is equal to change in internal energy with respect to change in internal energy, which cause 1. So the minus, and keeping S constant, change in temperature with respect to change in internal energy minus temperature, change in entropy with respect to change in internal energy. There forms it forms the equation number B. So we have just to follow the same process, having multiplied both sides, change in U, evaluating, we would able to get the change in Helmholtz free energy, which is equal to internal energy minus S entropy, change in temperature minus temperature, change in entropy, which forms the equation number C. So as we know, we have just to replace change in U with some other variables. So the change in U, we know that change in U is equal to temperature dava S minus P dava V. We have just to put on the equation number C. We could get the change in Helmholtz free energy, which is equal to minus P dava V minus S dava T, which forms equation number D. So following the fundamentals of differential equations, we have a dz is equal to m dava x plus n dava y. Similarly, we have just to differentiate by differential equations. So the change in dava m divided by dava y, keeping x constant, which is equal to dava n divided by dava x, keeping y constant. And we have got this from question number D, and we have just to make equal. P is equal to the m and S is equal to n. So then it will become minus of change in pressure with respect to change in temperature, having volume constant, and other side we have minus change in entropy with respect to change in volume, having temperature constant. Then we move forward to evaluate both sides signature minus sign signatures, cut them, because they will cut down each other. And then we have form change in pressure with respect to change in temperature, having volume constant, and then dava S divided by dava V, and then temperature is constant. Here we have discussed number 4 relationships,